Now finally, one of the things that we talked about is that we said that this really at its fundamental level was an energy transfer device. Now we can imagine that we could even graph what the energy is. Now we know that the energy is the total energy is going to be a constant. This is our constant. We saw that earlier. Now, of course, there will be some dissipation effects due to damping or whatever, but we're going to keep our model as ideal as possible. Now let's graph what that energy looks like. And what I'm going to try to do is I'm going to try and show how the energy transfers between potential and kinetic energy. Hopefully this will give us just one more window into how this device works. So in purple, we're going to show the kinetic energy. It's going to come down like this. We have a maximum kinetic energy right here because the velocity is at its maximum. It's going to come down and hit 0 right here because the velocity is 0. And then it's going to come back up here to its maximum and then back down to 0 when the velocity, and then back down to 0 when the velocity is 0. And finally, when we have a maximum velocity, here we go. So the total energy is constant. This bottom section in purple, that is kinetic energy. And in green, this is spring potential energy. We know kinetic energy is 1/2 mv squared. So we see that the kinetic energy is going to be some function of x dot squared, which in this case would be a cosine squared function. And we know that from what we've already learned about energy, where we see that this type of device is really an energy transfer device. So energy is moving from kinetic to potential, but the net energy of the system is unchanged. And for those of you interested in the math of the potential energy, we know that the potential energy of the spring is 1/2 kx squared. The position is a sine function, so we know that this potential energy graph follows a sine squared profile. And for those of you who want to take it up even another notch, if kinetic is cosine squared function and potential is sine squared function, we know that if we add them together, we get a constant, cosine squared plus sine squared. So we can see right here, when the spring is most compressed, we have a huge component of spring potential energy. And when the velocity is highest, when our kinetic energy is highest, we have very little potential energy. And so we can see, if we wanted to kind of evaluate it with the colors, we can see as time goes by, the total energy is remaining constant. However, potential and kinetic energies are changing very significantly, and we can see that in a really nice graphical way. Now let's take a step back at what we've seen. This model of a mass and a spring oscillating is so rich and full because it happens so often. So I'd like to summarize the critical components of this type of system. First, you need a restoring force that acts linearly with respect to position. You need a mass that wants to keep moving in the same direction in which it already was moving. And you need some sort of elasticity in the system. Finally, we need vibration, which comes in the form of some sort of perturbation. Now that we've explored the mathematics of a mass spring system, let's review that video again and see if we can understand what's happening on screen more fully. So I've put the video in slow motion for you so you can take your time seeing it quickly move to the right. The spring stretches, stores up the energy, and the force accelerates it back to the left. The spring on the right extends, increasing the force, increasing the acceleration, and pulling the mass back to the right. Take your time watching this, repeating it if you want, first looking at position as a function of time, then taking a look at velocity as a function of time, and finally acceleration as a function of time, until you start to see all of these working in concert in this experiment. In summary, I hope our exploration of harmonic oscillation has given you a much better intuitive feel for this physical phenomenon that happens all around us.